So today is 21st March and it's 7:45 a.m. and today I'm starting a new book and this is a different one. Usually I cover only non-technical books, but here we'll go through a technical book and read it line by line. Yeah, so let's see how it goes. So I'm reading using SQLite or SQLite by John Krabik. I'm not sure if I'm pronouncing the name right. So, since we are reading line by line, I'll also read the dedication statement to my great uncle Albert Uncle Al Krabik, 1918 to 1994. He took a young boy whose favorite question was why and taught him to ask the question how, who also, much to the dismay of his parents and the kitchen telephone, taught him the joy of answering that question, especially if it involved pilers or screwdrivers. It's beautiful. So let's actually skip over the table of contents. There are 10 chapters and 7 references section. So we'll go through the preface first. This book provides an introduction to the SQLite database product. SQLite is a zero configuration standalone relational database engine that is designed to be embedded directly into an application. Database instances are self-contained within a single file, allowing easy transport and simple setup. Using SQLite is primarily written for experienced software developers that have never had a particular need to learn about relational databases. For one reason or another, you may find yourself with a large data management task and are hoping a product like SQLite may provide the answer. To help you out, the various chapters cover the SQL language, the SQLite C programming API, and the basics of relational database design, giving you everything you need to successfully integrate SQLite into your applications and development work. The book is divided into two major sections. The first part is a traditional set of chapters that are primarily designed to be read in order. The first two chapters provide an in depth look at exactly what SQLite provides and how it can be used. The third chapter covers downloading and building the library. Chapters 4 and 5 provide an introduction to the SQL language, while Chapter 6 covers database design concepts. Chapter 7 covers the basics of the C API. Chapter 8 builds on that to cover more advanced topics such as storing times and dates, using SQLite from scripting languages, and utilizing some of the more advanced extensions. Chapters 9 and 10 cover writing your own custom SQL functions, extensions, and modules. To complete the picture, the 10 chapters are followed by several reference appendixes. These references cover all of the SQL commands, expressions, and the built-in functions supported by SQLite, as well as documentation for the complete SQLite API. SQLite versions. The first edition of this book covers, I think it should be covers, spell it COVOS, SQLite version 3.6.23.1. As this goes to press, work on SQLite version 3.7 is being finalized. SQLite 3.7 introduces a new transaction journal mode known as write-ahead logging or WAL. In some environments, WAL can provide better concurrent transaction performance than the current rollback journal. This performance comes at a cost. However, WAL has more restrictive operational requirements and requires more advanced support from the operating system. Once WAL has been fully tested and released, look for an article on the O'Reilly website that covers this new feature and how to get the most out of it. So there are a bunch of email lists. There is an example code download section. And this is an interesting part, like how we got here. Taking a book from an idea to a finished product involves a great many people. Although my name is on the cover, this could not have been possible without all their help. First, I would like to acknowledge the friendship and support of my primary editor, Mike Lukidis. Thanks to some mutual friends, I first started doing technical reviews for Mike over 8 years ago. Through the years, Mike gently encouraged me to take on my new own project. The first step in that path came nearly 3 years ago. I had downloaded a set of database exports from the Wikipedia project and was trying to devise a minimal database configuration that would hopefully cram nearly all the concurrent data onto a small flash storage card. The end goal was to provide a local copy of the Wikipedia articles on an ebook reader I had. SQLite was a natural choice. At some point, frustrated with trying to understand the correct call sequence, I threw my hands up and exclaimed, "Someone should write a book about this." Ding! The proverbial light bulb went off, and many late nights later, here we are. Behind Mike stands the whole staff of O'Reilly Media. Everyone I interacted with did their best to help me out, calm me down, and fix my problems, sometimes all at once. The production staff understands how to make life easy for the author so that we can focus on writing and leave the details to someone else. I would like to thank Dr. D. Richard Hipp, the creator and lead maintainer of SQLite. In addition to coordinating the continued development of SQLite and providing us with all the high quality software product, he was also gracious enough to answer numerous questions as well as review final draft of the manuscript. Some tricky spots went through several revisions and he was always quick to review things and get back to me with additional comments. A technical review was also done by John W. Marks. John is an old personal and professional friend with an enterprise class database experience. He has had the opportunity to mentor several experienced developers as they made their first journey into the relational database world. John provided very insightful feedback and was able to pinpoint areas that are often difficult for beginners to grasp. My final two technical reviewers were Jordan Hawker and Erin Moy. Although they are acknowledgeable developers, they were relatively new to the relational databases. As they went through the learning process, they kept me honest when I started to make too many assumptions and kept me on track when I started to skip ahead too quickly. I also owe a thank you to Mike Kulas and all my coworkers at Volition Inc. In addition to helping me find the right balance between my professional work and the book work, Mike helped me navigate our company's intellectual property policies, making sure everything was on the straight and narrow. Numerous coworkers also deserve a thank you for reviewing small sections, looking at code, asking lots of good questions, and otherwise putting up with me venting about not having enough time in the day. A tip of the hat goes out to the crew at Aroma Cafe in downtown Champaign, Illinois. They are just few blocks down my workplace, and a significant portion of this book was written at their coffee shop. Many thanks to Michael and his staff, including Kim, Sarah, Nicole, and Jerry, for always having a hot and creamy mocha ready. Finally, I owe a tremendous debt to my wife, Debbie Fligor, and our two sons. They were always willing to make time for me to write and showed enormous amounts of patience and understanding. They all gave more than I had any right to ask, and this accomplishment is as much theirs as it is mine. So there is some conventions about how text is used, and of course some directions about how to use the code examples from this book. So now we'll jump into chapter 1. What is SQLite? In the simplest terms, SQLite is a public domain software package that provides a relational database management system or RDMS. Relational database systems are used to store user-defined records in large tables in addition to data storage management. A database engine can process complex query commands that combine data from multiple tables to generate reports and data summaries. Other popular RDMS products include Oracle Database, IBM's DB2, and Microsoft SQL Server on the commercial side, with MySQL and PostgreSQL being popular open source products. The light in SQLite does not refer to its capabilities, rather, SQLite is lightweight when it comes to setup complexity, administrative overhead, and resource usage. SQLite is defined by the following features: serverless. SQLite does not require a separate server processor system to operate. SQLite library accesses its storage files directly. Zero configuration. No server means no setup. Creating a SQLite database instance is as easy as opening a file. Cross-platform. The entire database instance resides on a single cross-platform file requiring no administration. Self-contained. A single library contains the entire database system which integrates directly into a host application. Small runtime footprint. The default build is less than a megabyte of code and requires only a few megabytes of memory. With some adjustments, both the library size and memory use can be significantly reduced. Transactional. SQLite transactions are fully ACID compliant, allowing safe access from multiple processing threads. Full-featured. SQLite supports most of the query language features found in SQL 92 or SQL's 2 standard. Highly reliable. The SQLite development team takes code testing and verification very seriously. Overall, SQLite provides a very functional and flexible relational database environment that consumes minimal resources and creates minimal hassle for developers and users. Self-contained, no server required. Unlike most RDMMS products, SQLite does not have a client-server architecture. Most large-scale database systems have a large server package that makes up the database engine. The database server often consists of multiple processes that work in concert to manage client connections, file I/O, caches, query optimization, and query processing. A database instance typically consists of a large number of files organized into one or more directory trees on the server file system. In order to access the database, all of the files must be present and correct. This can make it somewhat difficult to move or reliably back up a database instance. All of these components require resources and support from the host computer. Best practices also dictate that the host system be configured with dedicated service user accounts, startup scripts, and dedicated storage, making the database server a very intrusive piece of software. For this reason and for performance concerns, it is customary to dedicate a host computer system solely for the database server software. To access the database, client software libraries are typically provided by the database vendor. These libraries must be integrated into any client application that wishes to access the database server. These client libraries provide APIs to find and connect to the database server, as well as set up and execute database queries and commands. The figure 1.1 shows how everything fits together in a typical client-server RDMMS. In contrast, SQLite has no separate server. The entire database engine is integrated directly into whatever application needs to access a database. The only shared resource among applications is a single database file as it sits on the disk. If you need to move or back up the database, you can simply copy the file. Figure 1.2 shows the SQLite infrastructure. By eliminating the server, a significant amount of complexity is removed. This simplifies the software components and nearly eliminates the need for advanced operating system support. Unlike a traditional RDMMS server that requires advanced multitasking and high-performance inter-process communication, SQLite requires little more than the ability to read and write some type of storage. So this is the difference as shown, as mentioned before, where we have in a traditional RDBMS client server architecture. So we have a client host where a user application there and then a DB client library is there. So that DB client library over the network connects to an RDMMS server, RDBMS server, and there is a server host where the DB files are stored. And RDBMS server basically abstracts these files away from all the client library, and this one handles like how to optimize the queries, how to handle multiple connections from the clients, and all of that stuff. So this becomes quite simplified in the SQLite interface where everything has happened within the client host. So you have a user application which has a SQLite library, and then there are multiple SQLite libraries, and then you have a single SQLite file which acts at you as your database source of truth. And all of them can connect to that. And this coordination, this is the only thing that you need to maintain in the client itself. This simplicity makes it fairly straightforward to port SQLite to just about any environment, including mobile phones, handheld media player, gaming consoles, and other devices where no traditional database system could ever dare to venture. SQLite is designed to be integrated directly into an executable. This eliminates the need for an external library and simplifies distribution and installation. Removing external dependencies also removes most versioning issues. If the SQLite code is built right into your application, you never have to worry about linking the correct version of a client library or that the client library is version compatible with the database server. Eliminating the server imposes some restrictions. However, SQLite is designed to address localized storage needs, such as a web server accessing a local database. This means it isn't well suited for situations where multiple client machines need to access a centralized database. That situation is more representative of a client server architecture and is better serviced by a database system that uses the same architecture. Single file database. SQLite packages the entire database into a single file. That single file contains the database layout as well as the actual data held in all different tables and indexes. The file format is cross-platform and can be accessed on any machine, regardless of native byte order or word size. Having the whole database in a single file makes it trivial to create, copy, or backup. The on-disk database image, the whole database can be emailed to a colleagues, posted to a web forum, or checked into a revision control system. Entire databases can be moved, modified, and shared with the same ease as a word processing document or spreadsheet file. There is no chance of a database becoming corrupt or unavailable because one of the dozen files were accidentally moved or renamed. Perhaps most importantly, computer users have grown to expect that a document project or other unit of application data is stored as a single file. Having the whole database in a single file allows applications to use database instances as documents, data stores, or preference data without contradicting customer expectations. Zero configuration. From an end user standpoint, SQLite requires nothing to install, nothing to configure, and nothing to worry about. While there are a fair number of tuning parameters available to developers, these are normally hidden from the end user. By eliminating the server and merging the database engine directly into your application, your customers never need to know they are using a database. It is quite practical to design an application so that selecting a file is the only customer interaction, an action they are already comfortable doing. Embedded device support. SQLite's small code size and conservative resource use makes it well suited for embedded systems running limited operating systems. The ANSI C source code tends toward an older, more conservative style that should be accepted by even the most eccentric embedded processor compiler. Using the default configuration, the compiled SQLite library is less than 700 KB on most platforms and requires less than 4 MB of memory to operate. By omitting the more advanced features, the library can often be trimmed to 300 KB or less. With minor configuration changes, the library can be made to function on less than 256 kilobytes of memory, making its total footprint not much more than half a megabyte plus data storage. SQLite expects only minimal support from its host environment and written in a very modular way. The internal memory allocator can be easily modified or swapped out, while all file and storage access is done through a virtual file system interface that can be modified to meet the needs and requirements of different platforms. In general, SQLite can be made to run on almost anything with a 32-bit processor. Unique features. SQLite offers several features not found in many other database systems. The most notable differences is that SQLite uses a dynamic type system for tables. The SQLite engine will allow you to put any value into nearly any column, regardless of type. This is a major departure from traditional database systems, which tend to be statically typed. In many ways, the dynamic type system in SQLite is similar to those found in popular scripting languages, which often have a single scalar type that can accept anything from integers to strings. In my own experience, the dynamic type system has solved many more problems than it has caused. Another useful feature is the ability to manipulate more than one database at a time. SQLite allows a single database connection to associate itself with multiple database files simultaneously. This allows SQLite to process SQL statements that bridge across multiple databases. This makes it trivial to join tables from different databases with a single query or bulk copy data with a single command. SQLite also has the ability to create fully in-memory databases. These are essentially database files that have no backing store and spend their entire lifetime within the file cache. While in-memory databases lack durability and do not provide full transaction support, they are very fast, assuming you have enough RAM, and are a great place to store temporary tables and other transient data. There are a number of other features that make SQLite extremely flexible. Many of these, like virtual tables, are based off similar features found in other products, but with their own unique twist. These features and extensions provide a number of powerful tools to adapt SQLite to your own particular problem or situation. Compatible license. SQLite and the SQLite code have no user license. It is not covered by the GNU General Public License (GPL) or any of the similar open source or slash free source licenses. Rather, the SQLite development team has chosen to place the SQLite source code in the public domain. This means that they have explicitly and deliberately relinquished any claim they have to copyright or ownership of the code or derived products. In short, this basically means that you can do whatever you want within the SQLite source code, short of claiming to owning it. The code and compiled libraries can be used in any way, modified in any way, redistributed in any way, and sold in any way. There are no restrictions and no requirements or obligations to make third-party changes or modifications available to the project or the public. The SQLite team takes this decision very seriously. Great care is taken to avoid any potential software patents or patented algorithms. All contributions to the SQLite source require a formal copyright release. Commercial contributions also require signed affidavits stating that the authors and, if applicable, their employers release their work into the public domain. All of this effort is taken to ensure that integrating SQLite into your product carries along minimal legal baggage or liability, making it a viable option for almost any development effort. Highly reliable. The purpose of a database is to keep your data safe and organized. The SQLite development team is aware that nobody will use a database product that has a reputation for being buggy or unreliable. To maintain a high level of reliability, the core SQLite library is aggressively tested before each release. In full, the standard SQLite test suites consist of over 10 million unit test and query test. The soak test, done prior to each release, consists of over 2.5 billion tests. The suite provides 100% statement coverage and 100% branch coverage, including edge case errors, such as out of memory and out of storage conditions. The test suite is designed to push the system to its specified limits and beyond, providing extensive coverage of both code and operating parameters. The high level of testing keeps the SQLite bug count relatively low. No software is perfect, but bugs that contribute to actual data loss or database corruption are fairly rare. Most bugs that escapes are performance related, where the database will do the right thing but in a wrong way, leading to longer runtimes. Strong testing also keeps backward compatibility extremely solid. The SQLite team takes backwards compatibility very seriously. File formats, SQL syntax, and programming APIs and behaviors have an extremely strong history of backwards compatibility. Updating to a new version of SQLite rarely causes compatibility problems. In addition to keeping the core library reliable, the extensive testing also frees the SQLite developers to be more experimental. Whole subsystems of the SQLite code can be and have been ripped out and updated or replaced with little concern about compatibility or functional differences, as long as all the tests pass. This allows the team to make significant changes with relatively little risk, constantly pushing the product and performance forward. Like so many other aspects of the SQLite design, fewer bugs means fewer problems and less to worry about. As much as any complex piece of software can, it just works. Chapter 2, Uses of SQLite. SQLite is remarkably flexible in both where it can be run and in how it can be used. This chapter will take a brief look at some of the roles SQLite is designed to fill. Some of these roles are similar to those taken by traditional client-server RDMMS products. Other roles take advantage of SQLite's size and ease of use, offering solutions that you might not consider with a full client-server database. Database Junior. Years of experience has taught developers that large client-server RDMMS product platforms are powerful tools for safely storing, organizing, and manipulating data. Unfortunately, most large RDMMS products are resource intensive and require a lot of upkeep. This boosts their performance and capacity, but it also limits how and where they can be practically deployed. SQLite is designed to fill in those gaps, providing the same powerful and familiar tools for safely storing, organizing, and manipulating data in smaller, more resource constrained environments. SQLite is designed to complement rather than replace larger RDMMS platforms in situations where simplicity and ease of use are more important than capacity and concurrency. This complementary role enables applications and tools to embrace relational data management, and the years of experience that come with it, even if they are running on smaller platforms without administrative oversight. Developers may laugh at the idea of installing MySQL on a desktop system or mobile phone just to support an address book application. But with SQLite, this not only becomes possible, it becomes entirely practical. Application files. Modern desktop applications typically deal with a significant number of files. Most applications and utilities have one or more preference files. There may also be system-wide and per-user configuration files, caches, and other data that must be tracked and stored. Document-based applications also need to store and access the actual document files. Using the SQLite library as an abstract storage layer has many advantages. A fair amount of application metadata, such as caches and state data and configuration data, fit well within the relational data model. This makes it relatively easy to create an appropriate database design that maps cleanly and easily into an application's internal data structures. In many cases, SQLite can also work well as a document file format. Rather than creating a custom document format, an application can simply use individual database instances to represent working documents. SQLite supports many standard data types, including Unicode text as well as arbitrary binary data fields that can store images or other raw data. Even if an application does not have particularly strong relational requirements, there are still significant advantages of using the SQLite library as a storage container. The SQLite library provides incremental updates that make it quick and easy to save small changes. The transaction system protects all file I/O against process termination and power disruption, nearly eliminating the possibility of file corruption. SQLite even provides its own file caching layer so that very large files can be opened and processed in a limited memory footprint without any additional work on the part of the application. SQLite database files are cross-platform, allowing easy migration. File contents can be easily and safely shared with other applications without worrying about the detailed file format specifications. The common file format also makes it easy for automated scripts or troubleshooting utilities to access the files. Multiple applications can even access the same file simultaneously, and the library will transparently take care of the required file locking and cache synchronization. The use of SQLite can also make debugging and troubleshooting much easier, as files can be inspected and manipulated with standard database tools. You can even use the standard tools to inspect and modify a database file as your application is using it. Similarly, test files can be programmatically generated outside the application, which is useful for automatic testing suites. Using an entire database instance as a document container may sound a bit unusual, but it is worth considering. The advantages are significant and should help a developer stay focused on the core of their application rather than worrying about file formats, caching, and data synchronization. Application cache. SQLite is capable of creating databases that are held entirely in memory. This is extremely useful for creating small, temporary databases that require no permanent storage. In-memory databases are often used to cache results pulled from a more traditional RDBMS server. An application may pull a subset of data from the remote database, place it into a temporary database, and then process multiple detailed searches and refinements against the local copy. This is particularly useful when processing type ahead suggestions or any other interactive element that requires very quick response times. Temporary databases can also be used to index and store nearly any type of interlinked cross-reference data rather than designing a set of complex runtime data structures, which might include multiple hash tables, trees, cross-reference pointers, and developer can simply design an appropriate database schema and load the data into the database. While it might seem odd to execute SQL statements in order to extract data from an in-memory data structure, it is surprisingly efficient and can reduce development time and complexity. A database also provides an upgrade path, making it trivial to grow the data beyond the available memory or persist the data across application runs simply by migrating to an on-disk database. Archives and data stores. SQLite makes it very easy to package complex datasets into a single easy to access fully cross-platform file. Having all the data in a single file makes it much easier to distribute or download large multi-table data stores such as large dictionaries or geolocation references. Unlike many RDMMS products, SQLite library is able to access read-only database files. This allows data stores to be read directly from an optical disk or other read-only file system. This is especially useful for systems with limited hard drive space, such as video game consoles. Client-server stand-in. SQLite works well as a stand-in database for those situations when a more robust RDBMS would normally be the right choice. Where it available, as SQLite can be especially useful for the demonstration and evolution of applications and tools that normally depend on a database. Consider a data analysis product that is designed to pull data from a relational database to generate reports and graphs. It can be difficult to offer downloads and evaluation copies of such software. Even if a download is available, the software must be configured and authorized to connect to a database that contains applicable data. This presents a significant barrier for a potential customer. Now consider an evaluation download that includes support for a bundled SQLite demonstration database. By simply downloading and running the software, customers can interact and experiment with a simple database. This makes the barrier of entry significantly lower, allowing a customer to go from downloading to running data in just a few seconds. Similar concerns apply to traditional sales and marketing demonstrations. Reliable network connectivity is often unavailable when doing on site demonstrations to potential clients, so it is a standard practice to run a local database server for demonstration purpose. Running a local database server consumes significant resources and administrative overhead. Database licenses may also be a concern. The use of SQLite eliminates these issues. The database becomes a background piece, allowing the demonstration to focus on the product. There are no database administration concerns. The simple file format also makes it easy to prepare customer specified datasets or show off product features that significantly modify the database. All this can be done by simply making a copy of the database file before proceeding. Beyond evaluations and demonstrations, SQLite support can be used to promote a light or personal edition of a larger product. Adding an entry-level product that is more suitable and cost-effective for smaller installations can open up a significant number of new customers by providing a low-cost, no-fuss introduction to the product line. SQLite support can even help with development and testing. SQLite databases are small and compact, allowing them to be attached to bug reports. They also provide an easy way to test a wide variety of situations, allowing a product to be tested against hundreds, if not thousands, of unique database instances. Even if a customer never sees a SQLite database, the integration time may easily pay for itself by improved testing and debugging capabilities. Teaching tool. For the student looking to learn SQL and the basics of relational models, SQLite provides an extremely accessible environment that is easy to set up, easy to use, and easy to share. SQLite offers a full-fledged relational system that supports nearly all of the core SQL language, yet requires no server setup, no administration, and no overhead. This allows students to focus on learning SQL and data manipulation without getting bogged down by server configuration and database maintenance. Given its compact size, it is simple to place a Windows, Mac OS X, and Linux version of the command line tools along with several databases onto a small flash drive with no installation process and fully cross-platform database files. This provides an on-the-go teaching environment that will work with nearly any computer. The database in a file architecture makes it easy for students to share their work. Whole database instances can be attached to an email posted to a discussion forum. The single file format also makes it trivial to backup work in progress, allowing students to experiment and explore different solutions without concern over losing data. Generic SQL engine. SQLite virtual tables allow a developer to define the contents of a table through code. By defining a set of callback functions that fetch and return rows and columns, developer can create a link between SQLite data processing engine and any data source. This allows SQLite to run queries against the data source without importing the data into a standard table. Virtual tables are an extremely useful way to generate reports or allow ad hoc queries against logs or any tabular dataset. Rather than writing a set of custom search or reporting tools, the data can simply be exposed to the SQLite engine. This allows reports and queries to be expressed in SQL, a language that many developers are already familiar with using. It also enables the use of generic database visualization tools and report generators. Chapter 10 shows how to build a virtual table module that provides direct access to live web server logs. Not the best choice. Although SQLite has proven itself extremely flexible, there are some roles that are outside of its design goals. While SQLite may be able to perform in these areas, it might not be the best fit. If you find yourself with any of these requirements, it may be more practical to consider it a more traditional client-server RDMS product. High transaction rates. SQLite is able to support moderate transaction rates, but it is not designed to support the level of concurrent access provided by many client-server RDBMS products. Many server systems are able to provide table-level or row-level locking, allowing multiple transactions to be processed in parallel without the risk of data loss. The concurrency protection offered by SQLite depends on file locks to protect against data loss. This model allows multiple database connections to access the database at the same time, but the whole database file must be locked in an exclusive mode to make any changes. As a result, while write transactions are serialized across all database connections, limiting the overall transaction rate. Depending on the size and complexity of your updates, SQLite might be able to handle a few hundred transactions per minute from a different processor and threads. If, however, you start to see performance problems or expect higher transaction rates, a client-server system is likely to provide better transaction performance. Extremely large datasets. It is not unusual to find SQLite databases that approach a dozen gigabytes or more, but there are some practical limits to the amount of data that can or should be stuffed into a SQLite database. Because SQLite puts everything into a single file and thus a single file system, very large datasets can stress the capability of the operating system or file system design. Although most modern file systems are capable of handling files that are a terabyte or larger, that doesn't mean they're very good at it. Many file systems see a significant drop in performance for random access patterns if the file starts to get into multiple gigabyte ranges. If you need to store and process several gigabytes or more of data, it might be wise to consider a more performance oriented product. Access control. A SQLite database has no authentication or authorization data. Instead, SQLite depends on file system permissions to control access to the raw database file. This essentially limits access to one of three states: complete read-write access, read-only access, or no access at all. Write access is absolute and allows both data modification and the ability to alter the structure of the database itself. While the SQLite API provides a basic application layer authorization mechanism, it is trivial to circumvent if the user has direct access to the database file. Overall, this makes SQLite unsuitable for sensitive data stores that require per user access control. SQLite is specifically designed without a network components and is best used as a local resource. There is no native support for providing access to multiple computers over a network, making it a poor choice as a client-server database system. Having multiple computers access a SQLite file through a shared memory is also problematic. Most network file systems have poor file locking facilities. Without the ability to properly lock the file and keep updates synchronized, the database file can easily become corrupt. This isn't to say that client-server systems can't utilize SQLite. For example, many web servers utilize SQLite. This works because all of the web server processes are running on the same machine and are all accessing the database file from local storage. Replication. SQLite has no internal support for database replication or redundancy. Simple replication can be achieved by copying the database file, but this must be done when nothing is attempting to modify the database. Replication systems can be built on top of the basic database API, but such systems tend to be somewhat fragile. Overall, if you are looking for real-time applications, especially at a transaction safe level, you will need to look at a more complex RDBMS platform. Most of these requirements get into the realm where complexity and administrative overhead is traded for capacity and performance. This makes sense for a large client-server RDBMS platform, but it is somewhat at odds with the SQLite design goals of staying simple and maintenance-free. To keep a frustration to a minimum, use the right tool for the job. Big name users. The SQLite website states that SQLite is the most widely deployed SQL database engine in the world. This is a pretty bold claim, especially considering that the most people think of relational database platforms, they usually think of names like Oracle, SQL Server, and MySQL. It is also a claim that is difficult to support with exact numbers because there are no license agreements or disclosure requirements. It is hard to guess just how many SQLite databases are out there. Nobody, including the SQLite development team, is fully aware of who is using SQLite and for what purposes. Regardless, the list of known SQLite users adds up to an impressive list. The Firefox web browser and the Thunderbird email client both use several SQLite databases to store cookies, history, preferences, and other account data. Many products from Skype, Adobe, and McAfee also utilize the SQLite engine. The SQLite library is also integrated into a number of popular scripting languages, including Python and PHP. Apple Inc. has heavily embraced SQLite, meaning that every iPhone, iPod Touch, and iPad, plus every copy of iTunes and many other Macintosh applications, all ship with several SQLite databases. The Symbian, Android, BlackBerry, and Palm web OS environments also provide native SQLite support, while WinCE has third party support. Chances are, if you have a smartphone, it has a number of SQLite databases stored on it. All of this adds up to millions, if not billions, of SQLite databases in the wild. No doubt that most of these databases only contain a few hundred kilobytes of data, but these low profile environments are exactly where SQLite is designed to thrive. Large client server RDBMS platforms have shown thousands of developers the power of relational data management systems. SQLite has brought that power out of the server room to the desktops and mobile devices of the world.